In this experiment, I'm going to be doing an acid-catalyzed dehydration reaction on a molecule called 2,3-dimethyl-2,3-butane-diol. That's this molecule right here. It's also referred to as pinacol. That's its common name. As I said, this is going to be an acid-catalyzed dehydration. We'll be using sulfuric acid with an alcohol to do an elimination reaction, which means that we would expect it to form an alkene. But as the name suggests, there's going to be some extra twist to this particular experiment that's going to give us a product that we don't expect. So the product that's being formed by this reaction is not an alkene, but something else. And one of your goals is to determine the structure of the molecule that's being made. Again, this does start out as an acid-catalyzed dehydration, so an alkene is synthesized in the process, but ultimately at the end, your molecule is something else. But this experiment uses a type of apparatus called a simple condensed condensation apparatus. It has two round bottom flasks connected by this glassware right here. The reagents, the pinacol and the acid, they're going to be placed inside this sort of upper flask right here. So I'll just put it right there. This is where we'll be putting the pinacol and the H2SO4. And then I will be putting a Bunsen burner, a heat source, underneath this. So we'll have like some nice flame here, and this is going to heat up essentially kind of like it's going to reflux, but notice that there isn't a condenser here. Now over here on this other side, there's this empty round bottom flask. This is referred to as the receiving flask. The heat that's being provided by the Bunsen burner is going to cause this reaction to take place. The molecule that we're synthesizing is going to be able to boil, but it's going to immediately condense itself down into this receiving flask. So this is where our product is going to be collected. And since we're not using a water condenser like we would normally use, the way that we're going to make sure that our product gets condensed into this flask and doesn't just all evaporate out to the top of this glassware, we're going to put that receiving flask inside an ice bath. I'm going to use a beaker for this, so there's just going to be ice cubes and water. This is going to create, obviously, a really cold environment right here, which creates a little bit of, I hesitate to say vacuum, but it creates a pressure differential so that, this is a lower pressure than this up here. This just has to do with the difference in temperature. Very hot, very cold. So the molecules are going to be sucked down into this receiving flask. The boiling point of pinacol and the boiling point of sulfuric acid is very high, so any unreacted pinacol and sulfuric acid are going to stay in this flask. They're not going to be boiling, but the product has a much lower boiling point, so it's going to evaporate, and then it's going to get itself sucked down into here. Once we get a good amount of the product collected, then I will be stopping, isolating that product, and we'll be characterizing it using infrared spectroscopy. We're going to be starting with 7.1 grams of pinacol. It is kind of a sticky, clumpy solid, which is probably going to make it pretty difficult to get 7.1 grams. There are some really large chunks inside this bottle. There's a huge chunk. These are really big pieces. We'll go with that, 7.266. Here's the 7 grams, approximately 7 grams of pinacol that I just measured out, and I'm going to transfer that into a 50 milliliter round bottom flask. If you recall, that pinacol was in really large chunks. I've already tried to break the chunks into smaller pieces, but as you can see, at least one of the pieces didn't get broken up into a small enough chunk to fit through the opening of the round bottom flask. The other chemical that I'm going to be adding is 3 molar sulfuric acid. I've got 20 milliliters already measured out, and I'm going to transfer that into the round bottom flask. And as I do this, I'm going to be pouring it around the opening of the flask to help rinse down any of the pinacol that kind of got stuck in the opening as I was trying to transfer it into the round bottom flask. The last component is a boiling chip. This is just a small rock. It is not a reagent, so it's not going to be used in the reaction. It's just placed in there to help the solution boil more evenly. Sometimes we use boiling chips in place of magnetic stir bars when we're not going to be doing magnetic stirring. So now I'm going to be assembling the glassware. This is an adapter. The adapter goes into the opening of the round bottom flask. It just allows, like as the name implies, it allows us to connect different pieces of glassware together. Sometimes a thermometer is placed inside these adapters. We won't be using a thermometer in this situation. Now, one of the challenges of assembling the glassware for this particular reaction is that I'm not going to be able to use Keck clips at all. The Keck clips are those little blue clips that help hold the pieces of glassware together. The reason for that is that I'm using a Bunsen burner, like that direct source open flame, and the Keck clips, they don't hold up to that much heat, so they just melt. So because I'm not using the Keck clips, I'm going to be making sure that I have maybe a little bit extra grease to help hold the glassware together. This is the second piece that I'm attaching. This is another adapter. This is what's going to ultimately connect to the receiving flask. Now notice that this adapter has a little spout on the end of it, just one spout. So not for water. Looks kind of like something that we might plug a vacuum into. That little spout on the end is used to hold what's called a drying tube. That would be something that we would use if we were not doing this reaction inside a fume hood. A drying tube is used to help absorb any smells or fumes that are coming off of the reaction. But since this reaction is being done inside a ventilation hood or a fume hood, I don't need to attach anything to that little port, that little opening. So there's my receiving flask, and I've got it nestled inside a beaker. The beaker is going to get filled up with some ice cubes. Remember, we want to have this round bottom flask nice and cold to help create a pressure differential so that our fumes get sucked down into that receiving flask. And again, notice that nothing is being held together with Keck clips, which makes this reaction a little bit more stressful because the grease that is used to hold the joints together, it's not sticky, so it's not really connecting and securing the glassware. Right now it's just all kind of dangling. So as this reaction goes along, I'm going to be monitoring it more than normal to make sure that the glassware is not slipping apart from itself. Now that top I just pointed at is open. I am going to cover it up with some foil to help minimize the amount of stuff that escapes during this reaction. So now everything is ready. It's time to connect the Bunsen burner. Bunsen burners in fume hoods are sometimes a little bit tricky. The ventilation makes it sometimes a little hard to light them and to keep them lit, and you'll see that I'll struggle with that a little bit initially here. Positioning this Bunsen burner underneath the round bottom flask, the goal here is that I want to use gentle heat. I don't want to use this like a blowtorch. So I want to make sure that the blue tip of the flame is not too close to the round bottom flask because I don't want to heat it up too much. And the way that I have it positioned right now is you see that the blue tip is right at the bottom of the round bottom flask. That's way too close. The solution is going to get way too hot. What I don't want is to accidentally boil any of the sulfuric acid or the pinacol. Remember, we only want our product to be boiling out of solution. So we want this to be heating gently, not heating violently, and that's tricky to do with a Bunsen burner. So I've got everything raised up so that everything will be a little bit further away from the blue tip of the flame. And then something that you can't see just because of the perspective in this video is that I don't have that blue flame positioned directly underneath the round bottom flask. It's actually sitting a bit to the front. It's maybe 2 inches ahead or in front of the round bottom flask, and that's to avoid direct heat between the Bunsen burner and the round bottom flask, again because I don't want it getting too hot. You might be wondering why I'm even using a Bunsen burner in this case when I could have much better heat control with a hot plate. The only reason that we're not using a hot plate in this situation is because it's just there's no room for it. With that receiving flask needing to be in the ice bath, it's just not physically possible to have a hot plate underneath that reaction flask. So the only option here is to use a Bunsen burner. You just have to use it really carefully. Now this glassware is difficult to get positioned just right, and that's mostly because I can't use Keck clips. So the glassware kind of twists itself around. But once I get it into a spot that I like, I'm just basically gonna not touch it. So we're gonna let this sit and react for a while. There isn't a specific time here. We're just trying to get a good amount of product collected in that receiving flask. So this has been reacting for about 15 minutes, and I just wanted you to get a chance to see what it looks like. Gentle boil, vapors being transferred down into that receiving flask where a little bit of product is being collected. So this has been reacting for about an hour and a half, maybe 2 hours. There's a small amount of product inside that receiving flask. It's really hard to see the product in the receiving flask, not just on video, but also in person, because it's a colorless liquid that's inside a flask that's inside a beaker full of water, which is also a colorless liquid. But as I pull it out and set it aside, you can see there's a little bit of hazy liquid inside the bottom of that flask. That's our product. Now, the byproduct of this reaction is water, so it's safe to assume that there's some water inside that receiving flask. It's also possible that some pinacol made its way into the receiving flask, maybe even some sulfuric acid. So the next thing that we're going to do here is purify the product using an extraction technique in a separatory funnel. This will be a pretty simple extraction in the separatory funnel. There's not a lot of steps involved in this particular extraction. And I'm going to begin by using some deionized water to rinse out the inside of the round bottom flask. Remember, the byproduct of the reaction is water, so it's safe to add water. There's probably already some water to begin with. The water is heavier than the product, so the product is on the top layer inside the separatory funnel. The water is down on the bottom. The water is nice and clear. The product is kind of hazy. I'm going to begin by draining the water out. We're trying to purify our product, which is the top layer. So I'm going to drain the water out from the bottom of the separatory funnel into a waste beaker. My goal is to try to get all of the water out. So I'm going to get a little bit of product drained out at the same time. Now I'm going to wash this or rinse this with saturated sodium chloride, about 5 milliliters, except for I'm going to way overshoot that, so it's about 8 milliliters. Saturated sodium chloride is extremely polar, because it's water, which is polar, and it's got sodium chloride, which makes it even more polar. That's going to help remove any impurities that are inside that organic layer. I'm shaking, venting, allowing these two liquids to mix together. The saturated sodium chloride is down on the bottom layer. Notice that it's hazy now. The top layer, which contains our product, is clear, so that means that it's purifying. It's getting nice and pure. Once these layers have had a chance to kind of settle down, separate really well, I'm going to drain the bottom layer again. Remember, our product is on the top. The bottom is saturated sodium chloride and any waste that we're removing from our product. So I'm going to drain that bottom layer again, get all of it out. Look at that nice clear product. This is another rinse with saturated sodium chloride, same volume. Second time, just to verify that everything has been removed. It's pretty normal to do this technique 2 times, just to make sure that everything is getting taken out. And again, the saturated sodium chloride is down on the bottom, our product is on the top, nice and clear. Once those bubbles kind of get all broken up, then I'm going to drain the bottom layer again. All of these bottom layers I'm just draining into the same beaker because they are all just waste. And this time I want to make sure that all of the water, saturated sodium chloride, has been removed. It all needs to be gone. Now there's our clean and pure product inside that separatory funnel. I'm going to put that into a new beaker. And then the very last thing I'm going to do here is just add a little bit of drying agent, anhydrous sodium sulfate. This drying agent is going to suck up any water that might still be trapped inside the organic layer. When we add this drying agent to our beaker, we're just going to add a small scoop, make sure that we have granules that don't clump together. It's not taking a whole lot. I can see that I've got some free-floating granules down in there, which means that it's nice and dry. And my last goal is just to remove the liquid from that drying agent and put it into a fresh beaker. I didn't mention this, but the product is a liquid. And so this liquid that we see here is just our pure product. There's no solvent or anything like that. All right, we are ready to get a mass of this product. Now, what I've done is pre-weighed this beaker. The mass of the beaker is 29.431 grams. And so the difference here is going to be the mass of our product. The beaker with the product is 31.013 grams. We're going to take the IR of this product. This is a really smelly liquid, so that means it evaporates really fast, and so that means I need to work pretty quickly in the IR to make sure I get a spectrum capture before it all evaporates. I've already taken the background, and so we're just going straight to the IR. Now, for this particular product, I don't really want to measure the boiling point of this. Like, that is normally one of the ways that we identify it and also test its purity. But measuring the boiling point of a small amount of liquid is really a hassle. So instead of measuring the boiling point, I'm going to use the IR as the one and only way of determining the purity of the product and also the identity of the product. And since we don't know exactly what this molecule is, like that's part of this experiment, is figuring out what the molecule is, the only way that we're going to be able to analyze the purity of this is just by taking a look at the appearance of the IR. If the IR looks clean, which it doesn't have any kind of weird peaks in it, it looks really nice. This is a really good looking IR. And so just based on the clean appearance of the IR, I'm going to assume that this is pure. And that means I'm not going to measure the boiling point. It's very pure looking IR. And then we are going to identify the molecule based on just sort of proposing a mechanism for this reaction, theorizing what could actually be happening, and then matching that proposed product up with this particular IR. So I'm just going to save this so that we have this as reference, and we will work next on identifying the product.